Welcome to Spring LIB.
So, in this problem, we are given a combustion reaction of a hydrocarbon, which is burned in a limited amount of air and which is formed both carbon monoxide and carbon dioxide. And we are given the mass of carbon monoxide, carbon dioxide, and water, which is formed in this reaction. So, in first part of this reaction, we have to find out the empirical formula of the compound. So, to find out the empirical formula of the compound, first we have to know how many grams of carbon and hydrogen are in the compound, and we can find out the mass of carbon and hydrogen in the compound by calculating their mass in the products, which is carbon monoxide, carbon dioxide, and H2O. So from carbon monoxide and carbon dioxide we can find the mass of carbon, and from H2O we can find the mass of hydrogen. So what we will do first, we will find out the number of moles of carbon monoxide, carbon dioxide, and water which is produced. From there, we will find out the number of mole of carbon and hydrogen which is being produced. And from those number of moles, we will find the mass of carbon and hydrogen in gram. And these masses will be the mass of carbon and hydrogen in the original compound, and from their mass in original compound we can find the number of moles of carbon and number of moles of hydrogen. Then we will divide each number of moles by the smallest number of moles to get a simplest whole number ratio of carbon and hydrogen's mole number. From there we can find out the empirical formula of the hydrocarbon. So our first step will be to find out the number of mole of each product. So the number of mole of carbon monoxide produced will be the mass of carbon monoxide, which is 0.467 gram, over the molar mass of carbon monoxide, which is 28.01 gram per mole, and it will give us a value of 0.0167 mole. Now, since we can see that in one molecule of carbon monoxide we have one carbon atom, that means in 1 mole of carbon monoxide we will have 1 mole of carbon, and in 0.0167 mole of carbon monoxide we will have the same number of mole of carbon. So the number of mole of carbon here is also 0.0167 mole. And from here we can find the mass of carbon which is being produced in the form of carbon monoxide, which will be just the number of moles times the molar mass of carbon, which is 12.01 gram per mole. It will give us a value of 0.200 gram. So this is the mass of carbon which is being produced in the form of carbon monoxide. Now we'll find the mass of carbon in the form of carbon dioxide, and for that we'll find out the number of moles of carbon dioxide first, which is again the mass of carbon dioxide produced over the molar mass of carbon dioxide, which is 44.01 gram per mole, and this will give us a value of 0.0166 mole. Again, in one molecule of carbon dioxide we have one carbon, that means in this in a certain number of mole of carbon dioxide we will have the same number of mole of carbon dioxide. That means this is the number of mole of carbon in this much mole of carbon dioxide. And from here we can directly find out the mass of carbon here, which will be the number of mole of carbon in carbon dioxide, which is 0.0166 mole times the molar mass of carbon, which is 12.01 gram per mole. And from here we'll have again the same amount of carbon in carbon dioxide. So this is the amount of carbon which is being produced in the form of carbon dioxide. So the total carbon in the original hydrocarbon will be the sum of the carbon produced in the form of carbon monoxide and the mass of carbon which is produced in the form of carbon dioxide. So the total mass of carbon will be 0.22 gram plus 0.200 gram, which will give us 0.400 gram carbon. So this is the mass of carbon. Now we'll find out the mass of hydrogen. So for that, we need to find out the number of mole of water first, which is being produced. So the mass of water which is produced is 0.450 gram, and the molar mass of water is 18.016 gram per mole. So from here, we will have a value of 0.025 mole. Now this is the number of mole of H2O which is being produced. That means, and again we can see that in one molecule of H2O we have two hydrogen. That means in a certain number of mole of H2O we will have two times that mole of hydrogen. So the number of mole of hydrogen will be 2 times 0.025 mole, which will give us um, 0.050 mole of hydrogen. Now from here we can find the mass of hydrogen, which will be just this number of moles time um, the molar mass of hydrogen, which is 1.008 gram per mole. So it will give us a value of um, again 0. Approximately the same mass of hydrogen. So this is the mass of hydrogen which is being produced in the form of H2O, and since um, this is formed from the combustion of the original hydrocarbon, that means this is the mass of hydrogen in the original hydrocarbon too. Now we know the mass of carbon and hydrogen in the original hydrocarbon. So from here we can find the number of mole of carbon and hydrogen in the original hydrocarbon. So we will write the mass of carbon, which is 0.400, and mass of hydrogen is 0.050 gram. So these are the mass of carbon and hydrogen in the original hydrocarbon. Now we will find out their number of moles in the original hydrocarbon. So the number of mole of carbon will be 0.400 gram over the molar mass of hydrocarbon, is 12.01 gram per mole, and it will give us a value of 0.033 mole. And the number of mole of hydrogen will be the mass of hydrogen over the molar mass of hydrogen, which will give us a value of 0.050 mole. So now we will divide each number of mole by the smallest number of mole, and from here you can see that the smallest number of mole is this. So we'll divide each number of mole by the smallest number of mole to get the simplest whole number ratio. So the whole number ratio for carbon will be 0.033 mole over 0.033 mole, which will give us a value of 1. And for hydrogen, it will be 0.050 mole over 0.033 mole, which will give us a value of 1.52. So since we need a simplest whole number ratio, And since this is not a whole number, we have to convert this to a whole number. And the smallest possible whole number we can convert it to is by multiplying by 2, which will give us approximately 3 here. And since we are multiplying this by 2, we have to multiply the ratio of carbon by 2 also, which will give us value of 2. So that means the simplest whole number ratio of carbon and hydrogen here is 2 is to 3. That means the empirical formula will be C2H3. So this is the empirical formula of the hydrocarbon we are given here. Now in the second part of the question, we have to find out the mass of oxygen which is provided. So as we know that from the law of conservation of mass, the mass of reactants is equal to the mass of products. So we know the all the masses of products and we know the other reactant mass. So just subtracting the mass of the other reactant from the sum of the mass of products, we can find the mass of oxygen um, which is taken part in this reaction. The mass of oxygen will be the sum of the mass of the products upon 467 gram plus 0.733 gram plus 0.450 grams. So this is the total mass of the products minus the mass of other reactant or the hydrocarbon, which is 0.450 gram, and this will give us a value of 1.200 gram O2. That means this is the mass of oxygen which has taken part in the reaction. Now in third part of the problem, we have to find out how much more oxygen we would require to completely combust the hydrocarbon. So in case of complete combustion, we will not have any carbon monoxide being produced. That means there will be no carbon monoxide and all will be carbon dioxide. That means for a complete combustion, we need to convert the carbon monoxide which is produced um, to carbon dioxide. And if we want to balance this reaction, we have to put a 2 here, and then we have to put um, a 2 here. Then we'll have 2 carbon on each side and 4 oxygen on each side. So this is our balanced reaction equation. That means to to convert two molecule of carbon monoxide or 2 mole of carbon monoxide, we need 1 molecule or 1 mole of oxygen. That means we have to know how many moles of carbon monoxide we have being produced in the reaction given, and from there we have to find out how many more oxygen we would require for a complete uh, combustion of the hydrocarbon. So we have calculated the number of mole of carbon monoxide which is being formed here, which was, so here it is. So this is the number of mole of carbon monoxide we got here. So 0.0167 mole. So to convert this much mole of carbon monoxide, we will need since to convert 2 mole of carbon monoxide, we need 1 mole of oxygen. That means to convert this much mole of carbon monoxide, we'll need half of this mole of oxygen, which is ultimately 0. 0.0084 mole of oxygen. So we need this much mole of oxygen to for complete or to just convert the excess carbon monoxide which is being produced here. So we have to find out the mass of oxygen for this much mole of oxygen. So the mass of oxygen to convert the excess carbon monoxide will be equal to the number of mole of oxygen which is required is 0.0084 mole times the molar mass of oxygen. For O2 it is 32 gram per mole, which will give us a value of 0.267 gram O2. So this is the mass of oxygen which we need in excess um, to convert all the carbon monoxide being produced to carbon dioxide. So the total amount of oxygen which we need for a complete combustion will be equal to the mass of oxygen which was provided, which is this. So this much oxygen we were being provided in the reaction. So the total will be 1.200 gram plus this much oxygen which we need to convert the carbon monoxide being produced plus 0.267 gram. The total will be 1.467 gram oxygen. So this is the mass of oxygen which would have been required for a complete combustion of the hydrocarbon.